I would now like to combine the concepts of enthalpy and entropy together and talk about Gibbs free energy. Gibbs free energy combines delta H and delta S along with temperature to allow us to decide if a reaction is going to be spontaneous or non-spontaneous. Well, first of all, let me explain what I mean by spontaneous. For example, what I just did, that's spontaneous. Now, speed and spontaneity are not necessarily two related phenomena. So, I mean, I can be spontaneous and slow as well. That's spontaneous as well. But when we're talking about spontaneous chemical reactions, what we're talking about is pretty much reactions that are just going to pretty much start on their own. Alright, this is all going to be decided by the signs of the delta H and delta S values that we're talking about. And it all comes to fruition in this table here. But what I want to do is talk about why the values in this table come out the way that they do. First of all, let's talk about the situation, and this is the most favorable situation for chemical reactions, and that's when we have a negative delta H and a positive delta S. So a negative delta H is an exothermic reaction. Oops. This is exothermic. So reactions where the products are of lower energy than the reactants are usually going to be favorable type reactions. So we're talking about this sort of thing. Here's your products and here's your reactants, and there's your energy right there, and there's your reaction pathway. So these kinds of reactions are going to be favored usually. The other thing that's going to favor reactions is a positive delta S. And what we're saying there is that the products have more entropy than reactants. So what we're saying there is that there's more disorder in the products than there is in the reactants. So what I'm saying is that this is going to be a very favorable type situation for most reactions. Let's look at the effect that has on the sign of delta G. The formula for delta G is delta G equals delta H minus T delta S. And if we're saying that delta S is negative, so I'll just put a negative in there, minus T. Now T is in Kelvin, so temperature will always be positive. Because there's no such thing as a negative Kelvin temperature. So I'm just not going to worry about that, or I can just put it in positive times, and that's a positive value there that we're talking about. Now what I want you to see here is if you've got a negative value and you subtract what's clearly a positive value, then you are definitely going to be getting a negative value. And what we know about spontaneous processes is that they will always have a negative delta G naught value. And this example I'm showing you here is definitely going to lead to a spontaneous reaction, and it doesn't matter what the temperature is. There's no relationship between temperature and sign here. You're always going to end up with a negative value. So these kinds of reactions will always be spontaneous. Let me show you where the relationship of this to what's on that slide. So this is like a Cartesian type system. What we're talking about here is negative delta H's, that's exothermic processes, and positive delta S. So we're looking in this quadrant here, and as I said here, delta G is negative, so these kinds of reactions will always be spontaneous. Well, let's look at the worst case scenario for reactions then. The worst case scenario for a reaction will be a delta H is positive, which is endothermic. So what we're looking at there is a situation where the reactants are lower energy than the products. So we've got reactants, we've got products here. So we're looking at less stable products than we are reactants. So that's not particularly favorable, and we can make it even more unfavorable by making delta S negative. What that means is that there's more entropy in reactants than products. Alright, so now we plug this into our delta G minus T equals delta H minus T delta S. Delta H naught is positive, and we're looking at negative minus positive times negative. Alright, so T is always positive, delta S is negative here. Now what I want you to see is if we subtract a negative value, we're always going to be positive here. So positive plus positive, which will always be positive. And these kinds of reactions will be non-spontaneous. Alright, so we've got the worst of both worlds going here. We've got unfavorable situations with the delta H, and we've got unfavorable situations going on for delta S as well, if we're talking about reaction forming products. So this process would be non-spontaneous. Now we go back and take a look at the slide, and you can see again we've got a positive delta H and a negative delta S, and delta G naught will always be positive and always be non-spontaneous. Alright, let's look at what happens now if we combine the two. So what we can have is a favorable situation for one and an unfavorable situation for the other. And as you will see here, temperature will begin to play a role into whether or not these reactions are going to be spontaneous or non-spontaneous. Alright, let's look at a positive, a good situation for delta H. That is, we'll make the delta H negative. So this is exothermic, and that's good. But now we'll make the delta S negative as well. And that means that there's more entropy in reactants than the products. So I'll just write more entropy in reactants. Alright, so favorable, unfavorable. Alright, let's see what happens now when we plug that in to the delta G equation. So delta H is negative, and minus a positive value, that's for the T, times a negative value. Now here's what I want you to see, is that now whether this whole thing comes out to be positive or negative is entirely dependent on the value of T. So if we choose a low value of T, and just for kicks, I'm just going to say low value of T and we'll make it t equals 0. Then what's going to happen is that we're going to have negative minus, well, negative minus 0. So this would be spontaneous at low temperature. And the other way you can look at this, if you've got a negative value, you'll be effectively adding a value because you've got minus and negative here. And if this value is small, then what's happening is delta G naught will remain negative. However, if we make this now large, so we've got a large value of t, the reverse is going to occur. Large value of t, and that's going to be positive now, and the reaction will be non-spontaneous at high temperature. And what I'm saying here is you've got a negative value and you're effectively adding this because it's minus negative. If we make this very large, we put a value of say 1,000,000 in here or something like that, then what's going to happen is we're going to be adding a very large value to a smaller negative number. So the result is going to be positive. So that's why I'm saying for a large value of t, the reaction will be non-spontaneous. It will be a delta G will have a positive value. Alright, so let's see how that gels with the graph. And again, what we were talking about was a negative delta H and a negative delta S. So we're down in this region, and here's what it says. Delta G may be negative or positive. It'll be spontaneous at low temperature and non-spontaneous at high temperature, and that's what we predicted from that. Alright, let's look at the last case now. And what we've got here is a poor situation for the delta H. So we're looking at a positive value for delta H, that's endothermic. So that's not so great. But a good situation for the delta S, and we'll make that positive, which means more entropy in products. More entropy in products. And we plug that into our equation again. And we're going to have a positive value here, and we're going to be subtracting a positive multiplied by a positive. So here's what I want you to see. If we make t a small value, so we'll say a low value of t, if you'd like we can make it 0, but a low value of t, the delta G naught will be positive, and reaction will be non-spontaneous. Alright, so take a look at that. Let's say we've got a large value of positive, a large positive value here. If we subtract a smaller positive value, we're still going to have a positive value. So what I'm saying is, for a low value of t, even if we made it say 0, then this would be definitely be left with a positive value. So we'd be talking about a non-spontaneous process. High value of t, delta G naught will be negative and reactions will be spontaneous. And again, what we're looking at here is a positive, and then we're subtracting a very large positive value, then we will get a negative value, which will lead to a negative delta G, which will be a spontaneous process. So I guess the whole point of what I just did is to try and prove to you that you don't need to memorize this graph or this table here. You can actually figure out what the spontaneity is going to be based upon what you know about the signs of delta H and delta S in relation to delta G.